Hello, my name is Yuwei. I'm from the University of Tokyo. Today, I'm going to present to you our recent research on intrusion measurement and detection in line using plot-wise associative memory. Here's today's agenda. For the methodology, it will be broken down into three sections. First, what's associative memory? What's a whole field network? And the network traffic pattern representation with back signals. And finally, we will talk about the plot-wise intrusion measurement and detection. Malware spread through a local area network can infect lots of inner users, causing a great loss. Unfortunately, traditional knowledge-based detection approaches based on characteristics, malware signatures have shown limits with ever-changing, malicious network patterns and diverse network environments. The analysis and processing of such network traffic can be very time-consuming, need animals, humans' efforts. In recent years, due to the great ability in information extraction and representation, deep neural networks have been applied for network intrusion detection to improve systems adaptability. Non-memory-based neural networks consist of multiple layers of neurons, and usually training such complicated deep neural networks costs a lot of training time before being used for the inference. Different from the non-memory-based neural networks, the whole-field network consists of interconnected neurons with bidirectional weights between every two neurons, which contribute to the great content addressable memory, namely the ability to store and recall. Besides, it has the characteristics of efficient correlational information representation with less computation cost through the one-shot learning. Let's move on to the next section. The proposed methodology includes two separate paths: the pattern store or training phase, and the pattern recall or the test phase. For the pattern store, we employ a protocol-wise analytical approach to extract the patterns of various protocol traffic in the network, which are UP, TCP, and UDP. Then we represent these patterns of each protocol with the corresponding whole-field network. After storing these traffic patterns from the training set, we use the extracted patterns from the test set as the input of the trained whole-field network. I mean to reconstruct the stored patterns from the neural networks. Then, by evaluating the reconstruction results with the metric of divergency rates, we identify if a network event is malicious or benign. First, I'd like to clarify what's associative memory of the whole-field network. A whole-field network consists of neurons connected by symmetric weights. To store input patterns using one-shot learning, the neural network updates its weights based on the input patterns for reaching stable states in the dynamic systems of the model. Then the patterns were set down at various attractors of the dynamic systems. Each of these attractors have a basin of attraction. For inference, one test data falls inside the attractor's attraction region. The whole-field network will involve its dynamics to the corresponding attractors based on the Lyapunov function, which is the energy function. It means the neural network updates its weights with the direction for decreasing the overall system's energy for each step. For the interest of time, I will not discuss the definition of the equation here. If you are interested, you can look into our papers. We extract the protocol-wise information from collected network traffic and separate it into small chunks. Each record has a time interval of 1 second. Besides, as a feature for representing network traffic, the number of total packets transmitted is applied. In order to store these records of network traffic in a discrete whole-field network, where each neuron has only two possible values, namely the positive one and the negative one. As a result, we convert the records with a value equal to or larger than 1 to the positive one and the records with the value of 0 to negative 1 as the input of the Hall-field networks for the training. As aforementioned, a discrete Hall-field network employs one-shot learning. A discrete Hall-field network consisting of 940 connect neurons is used to store the various patterns of network traffic. For every 900 records from the dataset, we store them as an intact pattern to represent the network features with 900 seconds as a result. Once storing these patterns in the Hall-field networks, the weights are updated accordingly. The weights between every two nodes are bidirectional and symmetrical with the same values. As such, we can store these patterns with the relationships between the nodes of Hall-field networks by updating the weights. For the training, we randomly select a total of 90 patterns from the training set for each protocol type, which covers 45 benign patterns and 45 malicious patterns. For the pattern record, we employ two steps of energy evolution based on the synchrony methods, where the updates of each node state is conducted in succession with a random start node. Then the dynamics of the Hall-field network continue moving towards the state with lower energy and finally converge to a stable state with a minimum energy. As a result, the latent features in the noisy pattern are revealed through the evolving, and the intact patterns of it is reconstructed from the Hall-field network, as shown in the graph on the right-hand side. The next thing I would like to talk about is how to measure, thus detect malicious network activities through using a metric called the divergency rate. For each generated patterns from the test set, we use it as an input of the trained neural networks to compute the divergency rates with respect to the various protocols, which measure abnormality concerning a specified protocol. In this equation, the capital M means the total number of malicious prototypes, and the capitalized N means the total number of the benign prototypes. Si is the similarity of the test pattern with the malicious prototype I. Sg is the similarity of the test pattern with the benign prototype J. Then by further aggregating the computed divergency rates for the app, TCP, and the UDP, we can obtain the overall abnormality of the input. In this equation for computing the divergency rates, we apply the maximum value as the output. That's because if any of the protocol-wise divergency rates surpasses the threshold for classification, it should be considered as malicious. In contrast, only when all the computed rates are below the threshold, these network events can be benign. For the evaluation, we collected network traffic data in a line of the institute, where a workstation was set up for data collection, and simultaneously, another one was set up for operating the various types of port scans. In this regard, we collected 1 day's network traffic data for each of these port scans, and a total of 2 days benign traffic data was collected. The training set consists of 1 day's benign data and suspicious data using the default scan, while the test set consists of the 1 day's benign data, and 1 day's suspicious data for each of the other types port scans. As such, we conducted the performance evaluation by computing the divergency rates to show the abnormality changes at different time points in a day. As shown in this radar chart, the blue lines shows the computed divergency rate results at different time, and the red lines shows the threshold used for classifying a network event between the benign and the malicious. We can see the obvious differences lie in the benign patterns and the malicious patterns. In addition, we employed as a metric the recall to evaluate the detection performance of the scheme. The recall is the parameter that is used to show how many relevant network events are successfully classified in all the relevant network events from the dataset. Finally, a average validation recall score of 0.959 was achieved for classifying these various types of network events based on the protocol-wise associative memory. The divergency spectrum in this table shows the different levels of abnormality with respect to different event types, whereas the benign has a minimum divergency rates of minus 0.0762. In contrast, the UDP default scan in this table shows a maximum rate of 0.1567. To conclude, associative memory-based intrusion detection system inline was proposed with the protocol-wise discrete whole-field networks. The stored prototype benign and malicious network traffic patterns within the whole-field networks were reconstructed from partial contents hidden in the noisy network traffic. By evaluating the system with the divergency rates and the recall, we measured the detection of various port scans inline. Finally, achieving an unbiased validation recall score of 0.959. Though malicious network traffic is limited to the port scans in the experiments, the method provides a novel solution to future network traffic pattern representation and memorization with the efficiency and adaptability. That brings us to the end of this presentation. I'd like to thank you for your attention today. I'd love to answer any questions you have now.